Actually, this is the first time I give a tutorial in such a huge room. So the problem is, I don't know how to use a pointer to indicate the content, right? So how to solve it? I just go to other rooms to say, okay, how the other tutorial speakers deal with that, and then I learned that okay, they use the mouse here, right? Okay, so I just use mouse in this tutorial. But why I just tell you this process? Because I want to help you to make stable prediction. So next time when you see me in other venues, in other conferences, you may tell, okay, if other tutorials use the pointer, then Peng will use the pointer. If others use a mouse, I will use mouse, okay? I would say this is not a stable prediction model, right? Because this is actually just based on what you observed, the correlation, okay? But the true model is, okay, so because it's a huge room, so other speakers use a mouse. Because it's a huge room, then I use a mouse, right? So if you just use this kind of feature to predict my next behavior, I would say this is a stable predictive model, right? So that's why we want to give this tutorial. Actually, the goal of this tutorial is just to try to bring the causality into learning, and how can we do better learning or better prediction in the sense of stability with inspirations from the causal inference. So that's the background of the tutorial, okay? So the machine learning now, of course, is quite popular and has been widely used in many application scenarios, right? Just think about your daily life, right? When you wake up at your home, just at 8 a.m., sorry. For me, jet lag may be 8 p.m. So the first thing you want to check is the weather, right? And then in the weather forecasting, actually there is a predictive model there, right? And then you go on the road, you go to your office, and in the process you need to guide by the GPS, and the GPS will tell you, okay, in 10 minutes somewhere will be a traffic jam. Right? Then that's a predictive model, right? And then you arrived at your company, and then you need to check in with your face, right? So this is a face recognition there, right? And then at 10 a.m., you start to do some research, and recently you're interested in computational social science. So you just go to the Google Scholar to search the article, and then there is a ranking problem there, right? This is a retrieval problem. This is also the learning. And then in the 4 p.m., you think that, okay, I need to learn more things. And then you just go to Amazon to buy some new book. And then there is a recommendation engine to support this kind of service, right? And then you finish, you want to hang out, you want to enjoy your food, right? And then you go to Yelp. And then they will recommend some good restaurants nearby you, right? And then, okay, you just pick up one to enjoy. And then you go back home, you enjoy your leisure time, right? And then you just turn on your TV, and there is a TV show recommendation system there, right? So you just think, okay, all day life. Actually, the machine learning techniques are impacting our daily life in a very ubiquitous way, right? But one thing is that, have you ever thought, what if the machine learning make a mistake? What if the machine learning just recommend a wrong movie that you're totally you're not interested in? Then what's the problem? Actually, I think that would not be a big deal, right? Because this will only make the company to earn less money. That's not a big deal, right? So in the years ago, we just pay attention to the precision. We just do some performance-driven optimization on the on the machine learning techniques, right? But now, actually nowadays, it's different. Now the machine learning techniques are trying to step into some risk-sensitive areas, right? Such as the healthcare, the law, and the fintech. Okay? So in these areas, if the machine learning technique make mistake, that's a big mistake. Okay? So in the health, a mistake means, okay, that's a health problem. You know, human health, of course, is the most important one, right? And in the law, a mistake means a justice problem, right? In the fintech, of course, it's still a money problem, but it's big money problem, right? So in all of these kind of areas, we think that, okay, we need to think about how should we pay attention to a machine learning technique, right? So in the previous study, we pay attention to the performance-driven optimization. But now, okay, the trend, the paradigm has changed. Okay, so now we need to pay more attention to the risks of the machine learning techniques. Okay, so that means we need to shift from the performance-driven to risk-sensitive machine learning techniques. Okay. Okay, so when we talk about the risk, then let's see what's the sources of the risk of machine learning techniques. So we think that one is that, okay, the explainability is a big problem of today's machine learning. Because most of our machine learning models are actually the black box model, right? We only care about the architecture and we care about the input and the output, but we can never explain the learning process, or we cannot even explain the output of a model, right? So when the algorithm tells us, okay, in this medical image, there is a disease, okay, here, okay, you just can choose to believe or not believe. Okay, so if you want to ask why there is a disease here, okay, the algorithm cannot tell you. Okay, then what's the problem? You know, we think that the final pattern of the AI or machine learning techniques in the future life maybe should be the human-in-the-loop pattern. Now, in this kind of risk-sensitive areas like the health, the military, the finance, and also the industry, okay, we can never purely rely on an algorithm to make a decision, right? The human should collaborate with the algorithm so that we can collaboratively to make a decision, right? Better decision. Then what's the very important precondition of the human-in-the-loop pattern is that, okay, the algorithm and the human, they need to have a common language. That means the output of the algorithm should be understandable for human. Right? If they cannot understand each other, then how can we collaborate, right? So this is actually, we think, okay, if in this kind of risk-sensitive area, we cannot explain the output of a model, this is quite a big risk, right, of today's machine learning technique. And the other problem is about the stability, okay? So we know that most of our machine learning methods are developed under a very ideal hypothesis, that is the IID, right? So the IID means, okay, the samples are drawn from the identical and independent distributions among the training and the testing. In other words, in more simpler words, that means, okay, we ask, okay, the testing distribution should be similar as the training distribution, okay? If this hypothesis is satisfied, no problem, right? But if the distribution systematically change from the training distribution, then there is no performance guarantee here, right? So that's a problem. Why? Because we can never control the generation of testing data, right? In real applications, we can never guarantee the testing distribution just follow the training distribution. Right? So then how can we make the performance of a model to be stable, right? So that's actually a very important problem to consider. So I will show you two very simple examples. One is just, okay, we just do dog classification. We just try to teach an algorithm to learn to recognize a dog. So this is training data, okay? So in the training data, you can observe the feature or the characteristic of the training distribution, that most of the dogs are on the grass. Some of them are not, but just a minority, right? Just on the ground, okay? So if you train this kind of model, if you train a model with this kind of training distribution, okay, of course we can train a model, right? Then we just use a trained model to predict some unseen data. If you give this kind of testing sample, no problem, right? The model can absolutely recognize this is the dog, right? If you just give this kind of testing sample, maybe. I cannot guarantee that the model can make correct classification, right? But if you give this kind of testing sample, no. The algorithm cannot recognize this is a dog, okay? So why? Because the distribution just too far from the training distribution, right? So this is a problem, okay? Another example is, okay, we just try to build up a cancer survival rate predictive model based on the city hospital data. So in the city hospital data, you will find out a very strong correlation. That is, okay, if a patient has a higher income, then he will have higher survival rate, right? So why? Because the level of treatment that you can get actually is determined by your income, by how much money you can pay, right? So if you just predict this kind of survival rate, the higher income, the income level actually is a quite strong predicator, right? But if you just try to apply this kind of model to the university hospital, then you will get problem. So why? Because in the university hospital, you know, the treatment level you can get is not determined by your income level, right? It's by research purpose, right? So in this scenario, if you just use, okay, the model that is trained in the city hospital data, then you will get a mistake here, right? So this is we say the stability problem, okay? So why we say that, okay, today's machine learning model has a problem of explainability and stability problem? Of course, you can say a lot of reasons, but in our opinion, okay, fundamental plausible reason is that, okay, today's machine learning models are based on correlation, right? The correlation actually is the very basics of most of the machine learning models today, okay? Of course, we know that correlation is not that reliable as we imagine, right? So this is a joke, okay? This is a meeting in a company, and the boss actually observed a very interesting correlation pattern that the sales volume is highly correlated with the number of shaved heads. Okay? Then the boss just asked all of the staff to take a reason. Right? Okay, of course this is not reasonable. Right? Okay, in more details, let's say, first is the correlation is not explainable. Right? So here is a very simple example that, okay, from our data, we observe that people who joined after falling out of a fishing boat is highly correlated with the marriage rate in Kentucky. Okay. So how can you explain this? Right? We cannot explain that. So if all of the models are based on this kind of correlation, then how can you explain the output of the model, right? That's not possible, right? Okay. The other one is, okay, correlation actually is unstable. So here you can see this is just just to mention the example, right? So based on this kind of training data, you will find out a very high correlation between the grass feature, just the red boxes here, right? The grass feature is highly correlated with the dog label, right? So when we just build up a model based on this kind of correlation, right? We just think that, okay, grass feature is highly has high predictive power for the dog classification, but if the environment change, if we apply this dog classifier into other environments, just like this kind of data, right? The dog at home, the dog on beach, the dog in the cage, okay? The grass feature cannot tell anything at all, right? That means when the environment change, when the distribution change, actually the correlation cannot, okay, provide a stable predictive power, right? So that's the problem, okay? So in this sense, we need to blame the correlation. Actually, we couldn't, because it's not the fault of correlation. It's not, it's the way we use it. We say that, okay, there are actually three sources of correlation in our data. One is just the causation. So here you see that T cause Y. Just an example is the summer caused the ice cream sales to increase, right? So this kind of a correlation is under the causal mechanism. And this kind of causation is actually stable and also explainable for us, right? And the second source of correlation is generated by confounding. So the confounding here is, okay, the X cause T and also the X cause Y. So you will see the T and the Y are correlated, right? An example is, okay, the income determine your financial product offer, and the income determine whether you accept it. So whether you accept it actually is not caused by the offer, but caused by your income, right? But in the data, you will say, okay, the product offer of the recommendation engine actually result in the accepted behavior. So you will say this is okay. This is a benefit, or this is the role of the recommendation system. But that's not true, right? So if you just observe you just consider the hidden variables here, you will see they are just the correlation. There are actually no causal effect in this sense. So this is another way of generating correlation. And this kind of correlation we think is a spurious correlation. It's not explainable and also it's not stable. Okay? So the third one is, okay, the correlation can be generated by sample selection bias. The sample selection bias here is just, we can just consider the example of the grass and the dog, right? You just sample the dogs on the grass. So you will observe the correlation between the grass and the dog, but they are actually, there is no causality there. So also this is a spurious correlation, right? But in our machine learning, actually we don't try to distinguish these three kind of sources, right? We just use them, right? So I would say that among these three sources of correlation, only the first one should be used for stable learning or for stable prediction, right? So this is actually our main idea. So when talk about the causality, I just want to first give a very practical definition on the causality. So here, the definition is, if we say that T cause Y, so if and only if we change T leads to a change in Y while keeping everything else constant, right? So when we, of course, we can measure the correlation between T and Y, there's no problem. But the difference is we need to control the X. We need to control everything else so that we can guarantee the change of Y is caused by the change of T, right? So this is actually the main idea of the causality. So the causal effect actually is defined as a magnitude by which Y is changed by a unit change in T. Of course, in the literature, there are many ways to define the causality. I would say that this definition is quite intuitive, and it's actually the interventionist interpretation of causality. Okay. Then what's the benefits if we just bring causality into learning? Okay, so I will just show you just the same example. So here we have three kind of variables. One is the T is a grass, and one is X is a dog nose, and one is a Y as a label. Okay, so if you just put them into this kind of triangle causal framework, okay, we will get the conclusion that, okay, the grass and the dog label, actually they are strongly correlated. But if you control the dog nose, you will find actually the grass and the label, they just have very weak causation, Okay? So if you just change the treatment to the diagnose, you will find, okay, the diagnose and the label, they have both strong correlation and also strong causation. So what's the difference? Okay? If we just use a graph feature, okay, in an IID scenario, there's no problem, right? Because the distribution doesn't change, so the correlation exists in the training data, still hold in the testing data, right? There is no problem. But if you just change the environment, then I would say that diagnose actually can do stable prediction, but the graph feature cannot, right? Because diagnose actually they cause an object to be a dog, right? So even you just throw the dog into air, we can recognize that's a dog, right? There's no problem. And another is if I just tell you that I predict that this is a dog, based on this kind of yellow features, okay? And the other model tell you that I predict that this is a dog based on this kind of red features. Which one is more explainable? I think it's quite obvious, right? So we think that the benefits of bringing causality into learning is that we can provide more explainable and more stable prediction, right? So here, of course, the explainable one is quite intuitive and quite straightforward. So in the later part, we will just focus more on the stable part. So how can we use the causality to do stable learning and stable prediction? Of course, in the literature, there has been a very rich body of research works on the causal inference, right? But whether they are ready for the learning or for the stable learning, I would say there are some gaps there. Okay, the first one is, okay, in the causal inference, actually it's quite difficult to evaluate the outcome of a causal model, right? Because in the causal, how to define causality, right? How can you say, okay, what you estimated is just the real true causal effect? Actually, this is a philosophical problem, right? So if we cannot provide a very objective evaluation criterion or benchmark, then there is a problem to advance this kind of direction. So we think from the point of learning, we think there is a problems there. So the other one is, okay, because the causality actually most of the researchers in this direction are from the statistics and also philosophy departments. So their data environment actually is a bit different from the learning environment. So in the learning environment, actually we call them the wild environments. So why we call them wild? Because the data are actually very high dimensional, very highly noisy, and also we often have just little prior knowledge on the model specification and also the confounding structures, right? So in this kind of wild environments, how can we do causal inference? And how can we discover the causality? I think this is a problem, right? And the third one is, okay, they actually have different targeting problem. So for the causal inference, they focus more on understanding the data, on understanding the underlying causal structure or the generation process of the observed data, right? But they actually care less on the prediction problem. But for learning, especially the supervised learning, actually all that we care is about prediction, right? So there is also a gap here. And in this line, so the causal inference, they care more about the depth of your understanding on the generation process, on the true model, on the causal structure. But for the learning, we care more about the scale and the prediction performance, right? So how to bridge the gap between the causality and learning, or even the stable learning? Actually, this is why we developed this tutorial, okay? So that's the whole motivation. And in the later part, I will first introduce some representative paradigms and also research works on the causal inference. And then we come to how can we bring this kind of causality into stable learning. And also we introduce just a benchmark data set to support the stable learning, okay? So this is the first part, the motivation. So is there any questions here?
Hi, so I was just wondering, what's your opinion on, like, do we need to build priors into our learning algorithms to learn specific causal mechanisms, or do you think that causal effects or like these things would emerge out of a specific training algorithm, let's say meta-learning or something? So is it possible that a model can develop causal behavior just through meta-learning or something?
So I'm sorry, I didn't just catch up your question. Do you mean that whether we can use causal learning to do...
So my question is, like, do we need to build in specific priors for causal effects to emerge?
Yeah.
Or is it possible that just learning algorithms could discover causal could show that causal mechanisms emerge just out of a learning algorithm without building in specific priors?
Thank you. Actually, when we do causality estimation or causal inference, actually we do need some priors. So later I will introduce the hypothesis when we do the causal inference. It's in the later part. And for your second question, so the causal actually try to find out the true model of the data generation, of the observed data. So if we can observe this kind of true model, and true model is quite stable and can be generalized into different domains. So in this sense, it can help to deal with, for example, the transfer learning problem and also the meta learning problem. I think this is a way to realize that. This is a very interesting direction. Yeah, I think maybe many of you are interested in the basic concepts or some basic idea in the causal inference. So maybe I should go to the second part and then I take the questions. Okay. Okay, then let's come to the causal inference part. So in the causal inferences, there are mainly two paradigms, paradigms. The first is a structural causal model, which was proposed by Professor Yuli Pro. So I would say that this kind of structural causal model is a quite strong graphical model to describe the causal mechanisms of a system, because it describes all of the dependence relationships among all of the variables in the system, right? So if you have this kind of structure, you can do a lot of things. One is that, okay, given for example, I want to estimate the causal effect of T on Y, then based on this graphical model, we can use the backdoor criterion to identify which variables you need to control for this causal identification, right? So this is actually one task. The other is, okay, if you want to know the causal effect, the quantity of the causal effect of T on Y, then you can just use the dual calculus, right, to do this kind of causal estimation. Because all of the, you can just imagine this is a data generative model, right? So all of the generation process has been incorporated or represented by this model. So that means when you do some intervention and you want to identify the causal structures, there is totally no problem, right? But the problem is, how can we discover this kind of causal structure? In a very specific domain, of course, we can just define this causal structure a priori by just some experts, right? But it's not very feasible, right? For example, in some very complicated scenarios, you can never define a very complete causal structure, a structural causal model by human, right? So a very important problem is how can we discover this kind of structure? Then the actually a representative researcher is Professor Bernard Sharkov, and they actually did a lot of work on the causal discovery. The causal discovery is trying to discover this kind of a structural causal model from the observed data. So in the observed data, we have a lot of variables there, and we need to test their independence. Okay, pairwise independence and also the conditional independence here. So the problem is this is a combinatorial problem, right? So if we say that in this framework, this is actually a very strong generative model with very strong expressive power, but the problem is it induces very high complexity. Okay, so this is a problem. And the other paradigm is potential outcome framework. It was proposed by Professor Donald Rubin. And this is actually a simpler, I think it's a simpler setting that, okay, in many cases, actually, we don't care about all of the structures among all of the variables, right? We just care, okay, the treatment effect of one targeting variable. For example, I just want to test whether a medicine is effective for one kind of disease, right? So in this sense, we can suppose, okay, there is a targeting variable here that is a treatment variable, right? And also we suppose that the confounders of T are known a priori, okay? So of course this is a simpler setting, and the computational complexity is affordable, but there is no free lunch. So we need some stronger assumptions. For example, we need that all of the confounders need to be observed. Okay. Of course, we can hardly guarantee this in some very challenging or complicated scenarios. But of course, this can make us practical in some real scenarios. So we would say that the potential outcome framework actually is more like a discriminative way to estimate the treatment's partial effect on the outcome. Right? So compared with this framework and also the structural causal model, I think from the point of learning, we would say that, okay, the potential outcome is more discriminative and the structural causal model is more generative. Okay? Okay, so in our tutorial, of course, we focus more on the learning and on the prediction. So we just we think that the potential outcome, the discriminative way is closer to our problem. So in the rest of part, I will just develop the tutorial based on the potential outcome framework. Okay. So first, I would first introduce the causal effect, some basic concepts in the causal effect estimation. The first is the treatment variable, right? Just the T here. So the T, you can just think that this is a medicine. Okay. So T1 means that take the medicine, and T0 means that you just take a placebo, right? So this is a T1 and T0. This is a treatment variable. And then we form the treated group and a control group. So in the treated group, every unit just take the medicine, and in the control group, every unit just takes the placebo, okay? Then we will have the potential outcome. So the Y here is just the cure rate of the disease, right? So the Y1 means that, okay, what about the cure rate in the treated group? And the Y0 means the cure rate in the control group, right? So if we have this data, then we can do an average causal effect estimation of the treatment. That means the ATE. So the ATE can be calculated by the expectation of Y1 minus 10, right? So this is actually a very simple framework. Then let's see what's the challenging problem. So the challenging problem is we meet a counterfactual problem here. So for every unit, we can just observe only one status of the unit, either Y1 or Y0, right? You cannot just at the same time to observe the output of one unit that takes the medicine and not takes the medicine, right? So you cannot do that because you can never step into the river twice, right? So here, this is a problem, right? So if you just, for each person, you can observe only one, then for different group, for example, for the treated group and for the control group, we cannot guarantee that the something else are consistent because they may have different kind of features and they may have different kind of profiles, right? So we cannot meet the two requirements. One is different groups, and one is keeping the others, something else, everything else to be constant, right? This is the problem. So ideal solution is that whether we can reason about a world, a counterfactual world that actually doesn't exist, right? So everything here in the counterfactual world is the same as a real world, except the treatment. For example, this is a real world, right? All of the persons here just take the medicine, and you need to reason a counterfactual world. So what if the person didn't take the medicine? You need to reason about that status. Okay? So this is a counterfactual. So the gold standard of this kind of counterfactual world reasoning is by the randomized experiments. So think, just imagine we have a very large population, and then we just randomly select one group of person to give them the medicine, and one group of person to give them the placebo, right? So because I just do random selection, so there is totally no bias, right, on everything else except the medicine, the treatment variable, right? But the problem is, the first problem is this is quite expensive. You need to recruit a very large population, right? This is quite expensive. And also this is sometimes is unethical. For example, you just want to testing the harmness of smoking. Then can you just randomly select a group of people to let them smoke, and the other group let them not smoke? You cannot do that, right? This is unethical. So the third one is in just a big data environment, actually, it's unrealistic. Just think about the example of the dog classification. We cannot control the data generation process. Right? Then how can we just do random experiments on this kind of data, right? So this is quite limited, right? So the way is, how can we solve them? It's just we need to do some observational studies in the causal inference, just based on the observed data, right? Not the controlled randomized experiments, okay? So that's the research focus, okay? So when we do that, of course, the key problem we want to solve is the counterfactual problem. Just try to resonate the y1 or the y0. So here the problem is, can we estimate the ATE just by directly comparing the average outcome between the treated and the control group? We would say that yes, if you just can do the randomized experiments so that we can guarantee that the X are the same, that everything else are the same, right? But you cannot do that with observational data because the X cannot be guaranteed to be the same on everything else, right? So that's the problem. So why we just need to guarantee the X should be the same? Because of the confounding effect. So here you can see this is an example, okay? So from this observed data, you can observe a pattern that the smokers usually have higher weights than the non-smokers. So you may draw a superficial conclusion that, okay, smoking can cause weight increasing, right? But here actually, there is a confounding effect. The confounding effect is brought by the age. So the age, actually, we know that when you grow older and older, you have much more things to worry about, right? So you just tend to smoke, right? And because you worry about more, so you will not have a very good life habit. So you just increase your weight, right? So actually, as an age that causes smoking, and its age causes you to increase the weight. So if we just consider this kind of a confounding effect, you will not get the conclusion that the smoking can actually cause the weight increasing, right? So that's the importance of confounding effect. So the thing that we need to do is how to balance the confounder's distribution between the treated group and also the control group, right? So that's actually the major theme of the causal inference. Okay, so Then we have 3 ways in the literature to deal with this problem for the confounder balancing. One is just a matching. So the matching is just, okay, we have big data. We have a lot of data. So in this large-scale data, we can sample 2 groups. That's, okay, they just have the same distribution on the X. Okay? We can do that, right? So for example, for these 2 groups, one is treated group and one is a control group. Okay? Every unit in the control group, we just try to find out a matched, okay, unit in the treated group. Okay? So they just have the similar X features. Okay? So for each treated unit in the treated group, we also find out a counterpart in the control group. So if for one treated unit, we cannot find out any counterparts in the control group, then we just discard it. Okay? So that's the matching. We can do this kind of matching to form the treated group and the control group and guarantee they have the similar X distribution. So formally, we can define it in this way. We just define a distance metric, right? A distance of xi and xj. And here we impose a threshold epsilon here just to select the matched pairs. And the paired units, of course, we can guarantee that everything else approximate constant, right? So from this sense, we tend to set a small epsilon here because this can bring less bias. But the problem is the smaller epsilon means that the less pairs of data that you can get. So this will actually bring higher variance, right? And also this kind of technique, actually, they fit for the low-dimensional settings. But in very high-dimensional settings, there will be very few exact matches, right? So this is a problem, okay? Of course, this is quite intuitive. The problem is we need to lose the assumption here. So that's why propensity score was proposed, okay? So the propensity score actually describes the probability of a unit to get treated, right, as pt equals to 1 given x. Okay? And Professor Donald Rubin actually proved that the propensity score is sufficient to control or summarize the information of confounders. Okay? That means if you just control the propensity score, it's equal. It's just an equal effect of controlling the x. Okay? So given the propensity score, we can guarantee that the treatment actually is orthogonal with the x. And also, given the propensity score, we can guarantee the treatment is orthogonal with a potential outcome. Okay? So that's the way to solve. So in the matching, we need to match two high-dimensional vectors. But in propensity score matching method, we only need to match 2 scores, right? So this is actually more friendly with a high-dimensional setting. So, but the problem is the propensity score actually cannot be observed, and we need to estimate the propensity score, right? So how can we estimate the propensity score? Actually, this is a supervised learning problem, because for every unit, we know whether it's treated. And also we know its X features, right? So we just only need to do something like a regression model, right, between the X and the T, so that the model can be used to estimate the propensity score. And conventionally, we just use a logistic regression because the treatment variable usually is just a binary variable, okay? So if we can estimate the propensity score, we can just matching the pairs by the distance between the propensity score. So here you can see in the matching, we just calculate the distance between xi and xj, but here we only need to compare the propensity score of x and the propensity score of j, right? So this is the way to solve it. And then in the propensity score in the matching methods, we have the high-dimensional challenge. But now we don't have the high-dimensional challenge, but we have the problem of propensity score estimation. So this is problem is whether we can correctly estimate the propensity score. And also in the propensity score matching and also the matching methods, actually this is something like a hard way to deal with that. And then the inverse of propensity weighting methods was proposed to do it in a soft way. The way is that we just don't do sample selection. We just do sample weighting. Okay? So we just assign different weights to different samples so that, okay, their X distribution can be balanced. Okay? So here, why the weighting with, why we need to weight with the inverse of a propensity score? The reason is that the propensity score actually induces the distribution bias on confounders. So here I will show you an example. So we have three kinds of units here. So for the units A, the propensity score is 0.7. That means if you have 10 units belonging to the type A, then you will get 7 of them to get treated and 3 of them to get untreated, the control, right? And for the B, for the type B, if the propensity score is 0.6, if you have 50 of them, then you will get 30 of them to get treated and 20 of them to untreated. Okay? So in this sense, you will find out in the treated group and in the control group, there is some distribution difference here, right? And the distribution difference actually is brought by the propensity score. Okay? So how can we just correct that? Okay? A way is that we can use the inverse of propensity score to reweight this kind of samples. Okay? So the weight is just represented in this way. That means in the treated group, you just use the inverse of the propensity score to weight. And in the control group, you just use 1 minus the propensity score, inverse of the 1 minus propensity score to weight. Okay? So if we do that, let's see the result. Okay? For the type A, you will get 10 units in the treated group and 10 units in the control group. And for the type B, you will get 50-50. And in the C, you will get 40 and 40. So after the reweighting, you will find out, these distributions are the same. Okay? So that's inverse of propensity score method. Okay, so if we can just using the weighting to balance the confounder distribution, then it's quite straightforward to calculate, to measure their ATE, right? We just, because it's just like, we have a new set of samples, but the samples are the same, but their weights are different from the original data set. And in this new data set, we can just directly apply the ATE there. Right? We just use a y1 minus y0 and to get the expectation to measure their ATE because their X has been balanced by the weights, right? So that's quite straightforward. So the interpretation here is that, IPW actually creates a pseudo population where the confounders are the same between the treated and the control group, right? But the requirements is that we need to do correct model specification for propensity score. That means the model form from the X to the T need to be correct. This is actually a very, a strong assumption, right? And the other one is when the propensity score close to 0 and 1, you will see a very high variance among the weights, right? And there is a problem that can cause that the model to be unstable. So the way to deal with that is, whether we can give a non-parametric solution, right? Because the model specification problem actually is inevitable in real applications. We can never guarantee that the model assumption, model specification just consistent with the true model, right? We cannot do that in most cases. So the problem is whether we can just skip the model specification, whether we can directly learn the sample weights that can balance the confounders distribution between treated and control groups, right? So that's the third line of research that is called the directly confounder balancing. So in the directly confounder balancing, the motivation is, okay, the distribution of a set of points actually can be represented by a collection of moments of the variables, right? Because the moments actually can uniquely determine the distributions, right? So whether we can learn the sample weights by directly balancing the confounder's moments. So here we just formulate it as an ATT problem, that is just the average treatment effect in the treated group, because in most cases we just care about, okay, the average effect in the treated group. For example, the group they take the medicine, right? Okay, so that's then in this setting we just need to impose a weight on the XC, and we ask, okay, the weighted XC, their moments are similar as the moments of the XT. Okay? So here we just use the average because we suppose all of the variables are just a binary. Okay? So in the binary setting, we can just use the first moment to describe, okay, their distributions here. Okay? So with this kind of moments, the sample weights can be learned without any model specification. Right? We can just learn the W. We do not have any assumption on the way to generate the W, right? So this is a difference. Okay. The problem is that, okay, if we just try to optimize this objective function, then there will be some like overfitting problem that can have a very high variance on the W, on the sample weights. So then the entropy balancing actually was proposed just the major objective to minimize the entropy of the W and subject to the balancing loss. So in this way, we can just guarantee the weights of the samples are just, okay, there is no very large variance here, right? So, but in this kind of methods, we just assume that we either know the confounders a priori or we regard all the variables as confounders, right? And also, we actually balance all of the confounders equally. We think that all of them are equally important, right? But we think that actually this is not necessarily true, right? For example, in the big data environments, you have a lot of environments, for example, millions of variables. We cannot suppose every variable is confounder of a given variable. Right? So how can we automatically identify the variables that are true confounders of a given variable? And also we think that different confounders actually they will bring different levels of confounding bias. So how can we treat them differentiatedly? So here we just propose the differentiated confounder balancing. So the idea is that, okay, just different confounders make different confounding bias. So here we just propose the new balancing loss here. So here just in this part, this is traditional balancing loss, right? But here we just impose a beta here. So the beta here is just the weights of different confounders. So we think that, okay, they actually can generate different levels of confounding bias. So the confounding weights, they determine which variable is confounder and its confounding contribution to the confounding bias. And the sample weights are designed for the confounder balancing. Okay? So in order to demonstrate that this is correct, we just formulate this with a very general problem that the outcome actually is generated by this kind of function of fx and t multiply gx and epsilon. So here you can see the gx actually is a causal effect, right? When the treatment is 1, then it's just take rows, and when t is 0, then there is no gx. Right. So you can just think about this in a signal way. Just the fx is a background signal, and the gx actually is a causal signal, right? Okay. So here we just think that, okay, the fx do not necessarily just depend on the input variables. And here we also allow some interactions of the input variables. That means, okay, there are some high order terms of the input variables here. So we define the fx in a more general way. Of course, we can simplify it by the augmented variables m here, right, to incorporate some nonlinear terms. So fx actually is alpha m is a linear form. And then under this function, if we estimate the ATT, you will see that, okay, the estimated ATT actually is a true ATT plus a Bayes term. And in this Bayes term actually is composed by two parts. One is a confounding bias, and the other is a confounder weights. Actually, this is proved by a theoretical analysis. Okay? That means, okay, if we just infer this in a series, okay, there should be an alpha there. Okay? So if alpha k is 0, that means alpha k, the corresponding variable is not a confounder. Right? And different confounders have different confounder weights, which is indicated by different values of our alpha k. And in our theory, we also prove that this alpha k actually is just the same as alpha m, just the coefficients of the m in the fx generation function. Okay, so this is the theory part. And then we just propose a model to simultaneously to learn the confounder weights beta and the sample weights w, right? And the w actually is just the same or similar as a traditional way, right? We just use a w so that the mcw can approximate the mt here, right? The moments, right? Of course, we impose a confounder a weights here, and also we ask the confounding weights can be used to approximate or to predict the y value, right? So that we can use, we can regress the y on the augmented variables, and then the derived coefficients can be used as a confounder weights here, right? So you can see that in this model, the entropy algorithm actually is just a special case of the differentiated confounder balancing if we just set the confounder weights to be a unit vector. Right? So this is actually a more general formulation of this problem. And finally, you can find out the difference in the performance. Right? So here you can see that this is a directly confounding balancing. This is a performance is a bias and also standard deviation. So if you just do the ATT just without considering any bias here, you are totally wrong, right? If you just use the IPW, this is the entropy balancing, and also this is a differentiated confounder. We can see that if you just consider, you try to differentiate different confounders, their weights, and also you try to identify which variables are the true confounders, then you will have better results on the ATT estimation. Okay? So that's the result. Okay. So finally, before concluding this section, I want to remind that for the causal inference, especially in the potential outcome framework, actually we have three assumptions here. The first is stable unit treatment value. That's the effect of one treatment of a treatment in a unit is independent of the treatment assignments of other units. That means that there is no feedback effect, right, in this system, in this setting. The second one is that the distribution of the treatment is independent of potential outcome when given the observed variables. That means actually all of the confounders should be observed a priori. Okay? So this is, quite strong assumption. And the third one is that each unit has non-zero probability to receive either treatment status when given the observed variables. Right? This is an overlap assumption. So when these three assumptions are satisfied, then we can do a correct estimation there. But of course, in real applications, I would say these three assumptions is not easy to be satisfied, right? Okay. So finally, let's summarize this section. In 2016, you know, that in the Academy of Science of the US, they organized a seminar that is called the Drawing Causal Inference from Big Data. So from that day, actually, a lot of researchers just start to look into the problem of how to estimate the causal inference in the wild environments. So a lot of progress have been made in this direction, but when we try to bring the causality into the learning, there are still some unsolved problems. The first is in the causal inference, we care more about a single variable's treatment effect. But in the prediction problem, actually, we are using a group of variables to make one prediction, right? So how to make it to be friendly for a group of variables? This is a problem. And also in the causal inference, especially the potential outcome, we usually consider the binary variables. But in learning, most of the variables are continuous variables. And also in the potential outcome, in the framework, we make some strong assumptions there. But for example, we have rich prior knowledge. But in the learning task, actually, we just have very weak assumptions there. So whether it's ready for learning, I would say not completely ready. But there are some ways, or we need to do some work from the learning end to think about how can we borrow power from the causality or causal inference. That's the point. And then we will go to the next part of how can we do that. So is there any question for this section?
I have a question regarding the confounders and treatment. So it looks like you actually need to manually define the treatment and confounders pre-hand, right? So I'm wondering, like a lot of machine learning, like you mentioned that in the fintech. So for example, you determine if a credit card has been approved or not. Sometimes it's a lot of features, a lot of data over there. My question is, like, how do you actually, first, how do you do it at scale? Second, how do you really differentiate the treatment of the causality and the confounders? Because it looks like you actually need to have some assumption over there than trying to do this exercise.
Yeah, actually the first problem, because for the causal inference, we just care about, for example, one treatment variable, and then we estimate the treatment cause effect on the outcome, right? So then we need to define the treatment variable. So in the learning task, we have many variables, so that's actually the focus of the second part. That is, how can we just, based on we stand in the machine learning, then how can we borrow the causality into the learning framework? Actually, that's the way to solve that, and we will introduce some representative works later. And your second problem is we need some assumptions to estimate the causal effect, right? I think the assumptions is not very that difficult because, of course, from the theoretical study, we need this kind of assumptions, right? But for the real applications in the wild environment, of course, it's not very easy to satisfy all of these kind of assumptions. But we can also try to sacrifice some, for example, the theoretical completeness and to attain some, for example, the gains in the performance. But I think the most difficult problem is you never know the ground truth in the causal effect estimation. So that's why we just think, okay, if we just bring the causality into learning and into the learning task, because learning is a well-defined problem, and there is a benchmark there, and there is a ground truth there, then maybe we can solve this kind of problem. So that's my answer. Okay.
Quick question about your KDD work. So if I understand it right, when you had this beta term, is that kind of like learning the graph structure of which of the x's are relevant for the t? You said that not all of the x's might actually influence the decision to treat or not. So can we think about that as like a sparse graph learning problem?
It's similar because you can see that we also impose a L1 regularizer to make the beta to be sparse. And the underlying hypothesis is that, okay, only a part of the variables actually are the confounders, right? And I don't think that it's a graph problem because we actually didn't consider the structures among these variables. We just care about their relations with the treatment variable or with the outcome variable, right? So I think this is a difference between the outcome, potential outcome framework with the structural causal model framework. So that's my answer. Yeah.
Thanks.
Quick question. So your treatment is, it's binary. You either took the pill or you didn't take the pill. A lot of times your confounding variables are continuous. Have you done work on doing that with continuous variables? And can you talk a little bit about that?
Yes, but actually we didn't do some deep research on the continuous variable problem, but of course, for example, you just take one medicine or two medicine pills. The natural problem should be a continuous variable. In the two line of research in both of the frameworks, actually, there are some recent research to try to address the boundary to the continuous variable. And in the potential outcome, they just use, for example, the expectation of the X to just simulate the moments consistency between the treatment and the control group try to use the expectation to describe that. But I actually don't have rich experience into addressing this problem. Sorry.
So my first question is, so whenever you have a graph, that's arrow means causality. Like in the graphs, you have random variables and arrows. So does an arrow means X, like points to Y means X has a causal effect on Y. Is that what does it mean?
Okay, I think that depends on how you constructed the graph.
So how do you define causality when you have a graph?
In the graph, of course, in the structural causal model, an arrow actually means a causal dependence there, right?
Okay,
but the precondition is you construct this kind of graph in a causal way, right?
Okay, so like that's for the first method you talk about, that you construct a graph in a causal way, then an arrow means causal effect.
Yeah.
And later on, the other method, the
potential outcome?
The potential outcome method, the model that you also have a graph like X, Y, T.
Yeah, yeah.
That does an arrow also means causality, causal effect in there?
Yeah.
So an arrow always means a causal effect?
Yeah.
Okay. I have another question. What does ATT means?
ATT means that, okay, average treatment effect in the treated group. We mean that, okay, for example, if you just try to test the effect of a medicine for a disease, you just want to measure the average treatment effect in the treated group. I mean the group of persons.
Oh, okay. So you constrain them to the subgroup that is got treated. Like,
So you need to control. You need to make the control group's distribution to approximate the treated group. But if you, of course, you can also do ATC, right? Average treatment effect in the control group. Then you just try to approximate the control distribution.
So why do you even consider this ATT quantity? Is that easier than the average treatment effect?
What do you mean?
Is that easier to estimate than the ATE?
No, I think there is no difference in the difficulty. Actually, just different scenarios, you have different interests. Actually, ATE is just the average of ATC and ATT. So actually, it's the same way to solve that. Yeah.
Earlier in the talk, you essentially took, I guess, like a Taylor expansion of some function f and then turned that into the variables m. So I guess, does this sort of setting work for more general, like nonlinear models without having to like add all of these many weights in this M matrix, or am I misunderstanding something?
You mean here, right?
Yeah.
Okay, so the M here actually is just because here we just need to make a model specification, right, between the T and the Y, right, X and the Y. So of course, a very convenient way is just to define a linear model here. But we know that linear model actually is a very strong assumption because it cannot incorporate a nonlinear relationship. So in order to address that, we just augment the variables with some nonlinear terms. So we just think that, okay, we can use a linear model with nonlinear term to approximate a nonlinear mapping function. So that's the idea of augmented variables. Okay. So then let's go to the second part, that's stable learning. So for the stable learning, I just borrow the figure from Professor Peng Cui. I think the tree structure is quite a good picture to describe the relationship between the stability, computability, and also the prediction. Here you can see that this is my understanding. So the stability part actually means the true model. Right? So what's the true model that generates this kind of data? Right? And for the computability, actually, it corresponds to the learning process. We just try to learn a model to fit this kind of data. Right? And of course, the prediction just corresponds to the prediction performance. So I would say that in the traditional learning, we are just starting from the data. And then we try to build up a model and make some prediction, right? So we are just doing some data fitting, right? So the data fitting process, actually, there is no problem, only if the environment is very stable. You just imagine that there is totally no wind, okay? So the tree just stands there, right? There is no problem, right? So if there is some wind, a moderate wind, because the tree actually has no root, so actually it's quite easy that the tree will crash down, right? Because we don't know the true model, right? So if the distribution, just the data distribution do not change, there is no problem, but there is some wind and the data distribution change, then actually there is totally no performance guarantee here, right? So what we call stable learning is trying to do this. We just are trying to identify the true model from the data, right? We try to find out the root. And then we use the root to do prediction, right? That's the stable prediction, and that's the stable learning concept, right? I think this is a quite different ways of thinking the problem, right? Okay. So you just try to position the stable learning with different from other lines of research. So here you can see that, okay, we have the training data. It's drawn from the distribution 1, right? And when we train a model, and then we test them, right? And in the testing, actually, there may be different distributions here, right? So if you train the model in distribution 1, and you optimize the testing accuracy also in distribution 1, this is RID learning. Right? This is most of the today's model, actually, we are doing that. Right? And if you just train the model from distribution 1 and you optimize the accuracy in the distribution N, this is a transfer learning. Right? So the precondition is, okay, you know the testing data actually is drawn from the distribution N. Right? So what's the stable learning? The stable learning is trying to minimize the variance of the accuracy in different distributions. Right? That's the stable learning. So you can see that, okay, this is different. So we think that the stable learning actually is more realistic and more practical in real applications because in the, I just said that in the beginning, we can never guarantee the distribution, testing distribution is the same or similar as the training distribution. And also, we cannot guarantee that the testing distribution is known, right? So how can you make a stable or guarantee that the stable performance in this kind of real setting? right? So that's the problem of a stable learning. So when we talk about stability, you may think about the robustness, right? Robust learning and robustness actually is quite popular in recent years of machine learning. So we try to distinguish these two concepts. So for the robustness, we think that, okay, it's focused more on the prediction performance over data perturbation, right? So it's quite prediction performance driven. So you just think that, okay, if my data is perturbed, then how can we guarantee the robust prediction performance? Okay, so this is robustness. But stability, so in the stability, we focus more on the true model that generate this kind of, the observed data, right? And we lay more emphasis on the bias, not prediction, right? We lay more emphasis on the bias of the estimated model and the true model, right? And of course, if we can estimate the true model correctly, we can guarantee robust prediction in different kind of distributions and in the data perturbation, right? So we think that, okay, stable learning is a way to realize robust prediction, and maybe it's a more intrinsic way to realize robust prediction. Because in many robust learning methods, actually we didn't just have the concept of the true model, but we just try to make some, for example, the adversarial training, right? We just simulate different kind of data augmentation, data perturbations, and then we learn a set of parameters that is stable in this kind of perturbated data, right? But the stable learning, we focus more on how to estimate the true model, okay? So in this line, actually there are some previous works. One is domain generalization and also invariance learning. So in this kind of setting, you can see that there is a global distribution here, right? And I suppose that in the training phase, we have different environments, and in different environments is each environment corresponds to a distribution of a subset of the global distribution. Okay, so this is our problem setting, and then we're trying to find out a model that try to predict the y given x such that the prediction works well or is robust for all possible environments. I mean, all possible environments include the trained environments and also some unseen test data. Okay, so that's the setting of the domain generalization and also invariant learning. Okay. So in the domain generalization, actually the basic assumption is the conditional probability, the p y given x, is stable for or invariant across different environments. Right. So if we have this kind of assumption, we just try to take the knowledge acquired from some related domains or related environments, and then apply it to previously unseen domains. Right. So this is a key idea. And then we just made some, of course, this is done by Professor Sharkov. They just made some reasonable technical assumptions, and then they proved that, okay, with probability at least 1 minus delta here, we can derive the hair bound of this loss. And this loss you can see is that, okay, in one given distribution that is a known distribution, the loss in this distribution can approximate the average loss in the known distributions, right? So that there is just a similar performance in the sense of the loss function, right? So they say that, okay, this actually is highly bounded by these two terms. One is the distribution variance. Right? The distribution variance means that, okay, you have some known environments, right? So how about the distribution variance in different environments? Actually, that's a term to determine the higher bound. And also the other term, actually, they just vanish in infinite sample size, okay? So the problem is, how can we estimate the beta so that, okay, we can reduce down the loss variance in different environments, okay? So actually, I would say that this setting is more in a robust learning way, because actually you're just trying to find out a set of coefficients or parameters that perform robustly in different known environments, right? And the problem they can solve is that if the unknown distribution, their bias has been incorporated by the known environments, known distributions, then they can work, right? But if the distribution change actually, they go beyond the known distributions, then actually they cannot solve this kind of problem. That means actually they can do interpolation, but they cannot do extrapolation, right? So that's the domain generalization method. And for the invariant prediction, actually they have a weaker assumption. They don't assume that the Py given x is stable, but they suppose that, okay, there exists a subset S belongs to x that is causal for the prediction of y. That means they think that, okay, Py given S is stable across all of the environments, okay? So this actually, the logic is, in the input variables, there are many variables there, but only a part of them are the causal variables for the output, for the outcome, right? So if we just assume the causal variables, the causal structures are stable or generalizable to different domains, different environments, different distributions, then of course we just use this kind of causal variable to make predictions can result in stable prediction, right? That's the main logic. So the way to solve this problem, of course, is just trying to identify the causal variables for the outcome, and then we can result to, for example, the structural causal model, right? If y is the outcome variable, then we can just use the parent node of the y to predict the y, right? So this is actually rely on the hypothesis that, okay, you can estimate or identify the causal variables correctly, and also there is a hypothesis that is the causal variables can just generalize, can generate the stable predictions in different environments, okay? Then actually, that's we would say that that's a variable selection way to solve this problem. Just select a subset of causal variables from all of the input variables. Another way to do that, we think, is also the sample reweighting from the potential outcome framework, right? So let's just revisit the direct confounder balancing. What we are doing is that given a feature t here, we just assign different weights to the samples so that the samples with t, that means the treated group and the control group, they have similar distributions of x, right? That's what we did in the confounder balancing, right? We just are trying to learn the weights, okay? So actually the result is, if we do this kind of sample reweighting, actually we can make a variable to be independent of other variables, right? Because for either the t is 1 or 0, x actually their distributions are the same. That means the t actually is independent of x, right? This enlightens us that, okay, by sample reweighting, we can just make a variable to be independent. And if the variable is independent, then we just need to do a direct regression of y on t, and then the coefficients actually correspond to the causal effect, right? So that's the intrinsic idea of the sample reweighting. But the problem is, for one given t, given one variable, we need a set of sample weights, right, to make it independent, right? Of course, this is not a natural learning setting. So the problem is, okay, whether we can find a set of sample weights that can decorrelate all of the variables, right? So if we can find out, okay, given any feature t, we can find out the same set of weights that can make, okay, each variable to be independent, or each variable, they are decorrelated, then actually we can use this kind of idea to do prediction, right? So in the traditional prediction or learning, we just depend on the input variables, and we never ask the relationships between the input variables, right? But now if we just use a sample reweighting, we can decorrelate all of these input variables, then actually we can predict with this kind of partial effect. And partial effect also can be regarded as a causal effect, right? Then we can predict with this causal variables, and we think that in this way it's stable across different environments, right? So this is actually the idea. So the key problem is whether there exists a set of ways that can decorrelate all of these variables, right? Then we just provide a theoretical analysis. And finally, we just prove that in the infinite sample size scenario case, there do exist a set of ways, W, that can make the input variables in X to be independent. Okay? All of the variables can be independent. So there exists this kind of sample weights. So just suppose if we can find out this sample weights, okay, then actually we just like the propensity score reweighting way, we just can form a new distribution, right? You just think that, okay, these samples, originally they are equally weighted, but now I just assign different weights to different samples, and then their distribution actually change. We just regard this change, the changed data points as a new set of data points, and then we can do every kinds of learning on this new set of data, right? And of course, in the learning process, we require that the learning model can incorporate different ways of these different samples. So here you can see that, okay, we can first try to learn the W from the observed data, right? So the X is all of the features excluding the treatment J, and W here is the sample weights, and the IJ here is an indicator of treatment status. So when we try to minimize this loss, actually we just trying to find out a W that can that can balance this treated and control groups for every variable. That means for each variable we can decompose, or we can just make them independent by this set of weights, right? So if we find out this set of weights, we can just naturally bridge with the learning model, right? Just the difference is in the previous learning model, we just regard each sample to be equally weighted, but now they have their own weights, right? So we can do, for example, the weighted logistic regression, right? And if you just do the weighted logistic regression, you will find the difference here. And if you don't do the weighting, the beta here actually is the correlation coefficients, right? But if you do the weighting, that means, okay, all of the variables, they have been decorrelated. Okay, then if you do the regression here, the beta actually they imply the causal contribution of a variable, right? So that's the difference. We can also, for example, to use this kind of sample reweighting strategy in some deep model, for example, the autoencoder, we map the input raw variables into a low-dimensional space, and then we can do balancing in the low-dimensional space, right? And then we can also decorrelate the variables to use them to make the stable prediction. So here I will show you some preliminary results here. So this is a data set, and in this data set, we just are trying to make it easy to generate this kind of distribution change, okay? So these images are just dogs, right? But we try to divide them into different contexts. For example, these are dogs in the water, this is in car, this is on the grass, right? And then in the learning process, we just use, for example, the first 3 contests to train the model, but we tested the model with the other 2 contests. That means we just want to validate whether a model can just do a good generalization. And this generalization is not in the sense of perturbation, but in the sense of distribution change, environmental change, right? So that's the key idea. So you can see that, okay, if we just use a causal model to do this, you will find a very interesting result here. So this is a different category, and the bar here means the context bias. That means the degree of the distribution change in this category. And the curve here is the causal, the relative improvement of the causal model over the correlation-based models. So here you can see that, okay, in the category that have higher context bias, the causal model will have a larger advantage. Right? So it's quite consistent. And also, we just try to visualize the highly weighted feature of causal model and also the causal learning model and also the correlation-based model. So here you can see the red boxes here are the highly weighted features in the causal model, and the green features are the highly weighted features in the correlation model. So, so the problem is we didn't do any object localization. Right? We just learn from the raw data. But finally, you can find that the highly weighted features in the causal model, they will just reside within the object region. Right? So if we just provide a prediction, an explanation of the prediction result, then I believe that this kind of red features is more explainable than the green features. Right? So that's the result here. Okay, so we just want to go further. And in the sense of, in the past, actually all of these previous works, they are from the causal problem and try to move to the learning, right? And then another way to think about this problem is whether we can think from the learning end and try to ask the question that why the learning model is not stable here, right? So the previous logic, right, is, okay, we can do sample reweighting, and then we can find out the independent variables. And from the independent variables, okay, we can find out the causal variables. And the hypothesis is the causal variables are stable, so we can make stable prediction, right? That's the previous logic. Okay. So we think that maybe there is a more direct logic. The logic is we can do sample reweighting, then we can find out the independent variables. And the independent variables can directly lead to stable prediction without the hypothesis of causal stability. Right? So that's another way to think about this problem. So we just want to think about, okay, the stable learning problem from the learning end. So why today's learning model, they cannot produce stable performance in different distributions. So here I just show you an example. Here is a PX, the training distribution. It's a Gaussian, right? So in most of the model, today's model, actually, we just optimize the overall loss, right, in this kind of distribution. Then we will get the result, of course, is that for the points in this region, we will have small prediction error, right? And for the points in this region, we will have large error. We regard them as corner points, right? So if we train a model in this way, just think about that, the distribution change into this. Then actually the previously corner points is not the corner points here as the mainstream points, right? So the model trained in the training data actually cannot guarantee a stable performance in this kind of different distributions, right? So the problem is, how can we guarantee a stable performance, right? So here we just think the idea is, if given the target y and the p input variables the x, so if we can just learn a predictive model which can achieve uniformly small error on any data point, then no matter how your distribution change, we can guarantee stable performance. Right? So that's the basic idea. That's the basic idea. Okay. So we try to analyze whether this is feasible or this is reasonable. So here we just consider a very simple linear regression setting, but with some misspecification bias. So here you can see that y is generated by beta x plus bx plus the epsilon the noise. Okay? So the bx here is a bias term, and the bias term is bounded by delta, so that okay, the generation of y is still dominated by the beta. Okay? It's not dominated by the bx. Okay? So then in this kind of model, if we can accurately estimate the beta bar with a property that bx is uniformly small for all x, then we can achieve the stable learning. Right? So if you just want to make a stable prediction, then the most safe way is just you use the beta bar to estimate. Right? Because the bx actually is a Bias term, and also the Bias term cannot be correctly estimated, maybe, right? So then we just do some theoretical analysis here, and we find that okay, the estimation error between beta hat and beta bar here, they are hair bounded in this way. Okay, so here you can see that okay, the gamma here is the gamma square is the smallest eigenvalue of the centered covariance matrix of X. And when the gamma square is very small, that means, okay, the bias term will go to infinity when there exists a perfect collinearity exists. Right? So the physical meaning of the smallest eigenvalue is that, okay, when we just project all of the data points on that eigen direction, then, okay, they are highly correlated, right? So we can actually use an eigenvalue to indicate the degree of collinearity in the input variables. When the smallest eigenvalue is very small, that means, okay, there exists a very strong collinearity in the input variables. So when there are perfect collinearity in the input variables, you can see that, okay, the estimation error will go to infinity. So in this sense, okay, that means that the collinearity actually is the main cause of the instability, right, in this kind of problem setting, right? Then we just do a toy example. So here you just assume we have a design matrix X, and the X is composed by two variables x1 and x2, and they are generated from a multivariate normal distribution, right? So here the sigma here is in this function, in this form, and the rho you can regard it as a controller to control the collinearity between the variables, right? So when the rho is very large, that means there are very strong collinearity in the input variables here, right? So then to induce the related the bias to make it related to the collinearity, we generate the bias term bx in this form. This form is bx equals to x multiply nu, right? And the nu here actually is an eigenvector that corresponds to the smallest eigenvalue, okay? So you can think that the Bias term actually is very sensitive to the collinearity. That means when the collinearity change, then, okay, the nu here will change, right? And the stronger collinearity will imply, okay, the bx will be stronger. So here we just do a simulation experiment. So here you can see that we just tune the values of rho to generate different smallest eigenvalues, right? From 0.9 to 0.1, that means, okay, it's increase the collinearity. And the stronger collinearity will bring higher estimation error. You can see the average bar here, right? And then, based on this, we change the distributions of the training distribution. Then they will have a variance here. And you can see that, okay, this kind of error, estimation error will be inflated, right? When very significantly when the collinearity is very strong, right? So all of this actually can demonstrate the collinearity actually is a key factor that make a linear model to be unstable, right? And then our goal is try to reduce the collinearity by sample reweighting, right? Just to reduce the collinearity, but not discover the causal models, right? So the idea is try to learn a new set of sample weights, the WX, to decorrelate the input variables and also increase the smallest eigenvalue, right? So of course, if we just do this kind of sample weights, we can just use a weighted least square estimation, right? So here you can see that, okay, so there is a WX here, right? If we hide it, this is just a normal least square, and now it's a weighted least square based on the original distribution. Actually, this is equivalent to another setting. That is, okay, we just use a weights to form a new distribution, right? And then in the new distribution, we just do the normal least square, right? This is equal, right? This is equal. So the problem is how can we find out an oracle distribution, the detailed here, which holds the desired property that, okay, all of the variables are decorrelated, or at least reduce their collinearity, right? So we just do it in this way. So this is original design matrix, right? And this is a target design matrix. We hope that in the target design matrix, okay, all of the variables, they have very weak collinearity or even no collinearity there. So we just do this that, okay, we can treat the different columns independently, and we perform random resampling. Okay, random resampling can guarantee, okay, this, okay, different, after the sampling, the different variables can be decorrelated, right? And then we can obtain a column decorrelated design matrix, X tilde here with the same marginal distribution as before, as the original design matrix, right? Then we can just use the density ratio estimation to get the WX. That means we have the target distribution, we have the original distribution, then how can we weight the original samples so that they can approximate the target distribution? Of course, a very straightforward way is just to do the density ratio estimation, right? Okay, after do that, this is a result. When we reduce the collinearity, we just use resampled, reweighted samples to learn the model. You can see that, okay, this is an estimation error. We compare with ordinary least square, the U lasso, I lasso, and many baselines. And you can see that we can significantly reduce the estimation error here. And if you just use this kind of estimated beta to do predictions, you will see a very stable, a relatively stable performance compared to other baseline methods. And if you just change the distribution and calculate their average performance and the variance between different distributions, you can get this figure, right? This is our method, and the average is reduced down, and also the variance is very small, right? So that's actually the stable prediction performance. Also, we just use this for some regression task in real data. You can also observe the differences, and also in some classification task. This is AUC, so similar pattern, right? Okay, So that work actually, the basic setting is that we have the input variables, and then we just try to reweight the samples to decorrelate the input variables. But the problem is, sometimes the input variables are not that good enough, right? So the more fundamental way is that whether we can learn representation space, and in this representation space, all of the variables are naturally decorrelated. That's actually the basic idea of the disentangled representation learning. Right? That is the main representative researcher in this field is Yoshua Bengio, right? And then actually we know that in deep learning they have the advantage that they can allow learning higher levels of abstraction. And the most notable advantage is that they can learn the representation space but not a predefined representation space. So if the higher level abstractions, they can disentangle the factor of variation, that means, okay, we can do very good generalization and transfer. And we can generate stable performance in different scenarios, right? And then they just, trying to do some research in this direction. And for example, when they train a model on the image classification, they will have different policies. For example, one policy is that whether we can control the light condition, right? So if we control the light condition or we change the level of light condition, we just constrain that in the representation space, only a small part of the neurons will be changed. So if we constrain the model learning process in this way, of course we can disentangle the different units in the representation space, and a subset of them may correspond to one disentangled factor, right? So this is actually a good way for the disentanglement representation learning, but the problem is they require very subtle design on the policy set, right? And in real settings, of course, this policy set is not at hand, right? So this is a problem. Okay, so I will just try to summarize this section. So we can see that the causal inference do provide some valuable insights for the stable learning, right? Many of them, for example, the decorrelation make the variables to be independent by sample reweighting. Actually, the initial idea comes from the causal inference. And another factor is complete causal structure means that we know we know the data generation process, and of course this can necessarily lead to stable prediction, right? But the problem is I just mentioned that we never have the ground truth about the underlying process, right? So if we can do that, of course this can solve all of the problems, but we do not have a very good benchmark ground truth to do that. And a stable learning, we think, can also help to advance the causal inference because they are just trying to reach the same goal with different means, right? Because the common problem is how to estimate the true model of the data generation, right? But the difference is in the stable learning as performance-driven. We have the ground truth, we have good benchmark, so that we can advance this field very fast. So we think that, okay, these two parts actually, they complement to each other. And as I just mentioned, the benchmark is very important, right? Especially for stable learning. But today, actually, there are a few data sets that can support this kind of distribution change, or you can control the distribution change of the data set, right? So that's a problem. So that's why we just, very quickly, I will go through, we just released a new image data set for the stable learning, okay? So in this data set, we just, first we want to say that actually in the image classification, we think that this is a very mature direction. But if you look into the performance, you will find some new problems there. So here we just calculate a metric that is called NI as the non-IID index. So it measures, okay, for each category, we just measure the difference between the training set and the testing set. Okay, so how different is the training and the testing? And then do a normalization here. Then you will find that, okay, actually in the ImageNet, different category, they have different NI index. Okay? And if you use the same model, the CNN model to predict or to do classification in different category, you will find this figure. In this figure, the bar means the NI value in this category, and the yellow curve means the error rate. Okay? So you will see that, okay, the error rate actually is perfectly correlated with the NI. That means, okay, actually in the categories that are non-ID, they have a high degree of non-ID, then the existing models actually cannot work very well, right? So that's the finding. So the problem is the existing data sets, including the Pascal, the ImageNet, the MS COCO, you just can calculate their NI in different categories, and then you will find all of these data sets, if you just do some random sampling, the NI is quite small, and the NI is uncontrollable. So if you want to simulate even more challenging distribution change, actually this kind of data set cannot provide you a flexible way to control the value of NI of the resulted data set. Okay? So we think that a data set for the non-ID or for support this kind of distribution change in image classification is highly demanded. So here we just construct a NICO data set, and in this data set, we provide the object label, and also we provide some contextual labels. For example, the object label is dog, the context label is on the grass or in the water, right? Something like that. And this is the structure of NICO. So in total, we have 2 superclasses, and in each superclass, we have 10 classes, and in each class, we provide 10 contests. So that we can generate diverse, meaningful, and overlapping contests here. So the data size is, for each superclass, we have 10,000 images, and for each class, we have about 1,000. So here is a snapshot of a sampled snapshot of the data set. You will see that for each category, we provide different contests here, right? At home, on beach, something like that. And then, based on this kind of data set, we can control the NI, right? So here we provide 3 means to generate the bias. One is a minimum bias, just compare with the ImageNet. We can just do some random sampling. And also we can realize the proportional bias. That is done by controlling the number of samples in each contest in the training and the testing. And also we can provide a compositional bias. That means, okay, in the training we use a subset and a subset of contexts, and in the testing we use another subset. Okay, so here you can see that even in the minimum bias, just to do some random sampling, okay, the average NI is just about 3.5, around that. And comparatively, in the ImageNet, it's just 2.7 or something like that. So that means, okay, in the NICO, actually we provide rich contextual and also more diverse distributions. So we will say that this is a more challenging data set. And in the proportional bias, by controlling different numbers of samples in different in categories between training and testing, you can see that we can control the NI from the 4.1 to 4.5, right? So you can control that, okay? And also, if you just using the compositional bias to control, then we can generate an even higher, approximate 5, right? NI value here, right? Okay, Finally, you can see the summary. So the summary is the ImageNet, their NI range is is between 2 and 2.5. And for the minimum bias, proportional bias, compositional bias, we can gradually increase the bias, right? And to generate a larger NI. So in this data set, actually we provide all of the flexibilities for you to generate different kind of a distribution change in different levels, right? So if you are interested in this data set, you can download it from this link. And also we have a manuscript to describe the details about this data set, okay? Finally, I will give you the conclusion. So we think that the predictive modeling is not only about the accuracy that we just pay all of our attention to, right? So the stability actually is quite critical for us to trust or to rely on a predictive model. So in the previous study, actually it has been demonstrated that the causality is useful in the stable prediction. But how to marry the causality with the predictive modeling effectively and also efficiently in very large-scale data, I think this is still an open problem and worth our more research. And finally, I would like to share this figure that for the causal inference, actually, we care more about debiasing, right? We care more about whether the estimating model is consistent with the true model. And in the stable learning, actually, we care more about the prediction performance. So you can see there is a natural progress along this line from the causal inference to the stable learning. Initially, the propensity score and the direct confounder balancing to the global balancing to the linear stable learning to provide some theoretical foundations for this field, and also for the disentangled learning to address some representation learning on the linearity problem, right? So here we think that, okay, there is still a very large space to explore in this direction, and I hope more and more researchers will join, okay? Finally, these are the references. If you want to know the details, you can refer to this. And also, finally, I want to acknowledge my collaborators, including my students, and also Bo Li from Tsinghua, and also our partner, Susan Ashley in the Stanford University. Okay, that's all. Thank you.
So I guess if I understand correctly, the stable learning that you define is basically with respect to the observed confounder. But I guess in practice, you could also have a hidden confounder. So do you think it's possible to have stable learning under a hidden confounder?
Yeah.
Thanks.
Yeah, that's actually why we just bring disentangled learning into this PBT. I think a fundamental way to solve this problem is just, okay, for example, you just input the model with very raw data. Right? We don't just extract the features on this raw data, you just input them into the model, and then we learn representations that is disentangled among each other, and this disentangled representation can well support the prediction. Actually, in this way, of course, for example, unobserved confounders problems or unobserved variables can be solved. But for our work, for example, in the linear model, of course, we assume that all of them are observed, but we think that much work can be done to solve this. Yeah.
I want to ask about the disentangling. So it's a very controversial topic, as you know. The work you mentioned, it sounds like they're artificially creating the data, so it's going to be disentangled by construction. But then there's a lot of work on unsupervised disentangling, beta VE, blah, 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 and it's like all very shaky because it's not identifiable, right? Mm-hmm. Your work in the linear models, you're doing this reweighting, and you're doing more work than just standard max likelihood estimation. So do you think any of the work in the deep learning literature is going to give you stable models if all they do is some maximization of a lower bound with a kind of generic regularizer? It seems to be missing some of the magic that you brought in to bear.
Yeah, this is quite a tough question, actually. But I agree that for the disentangled learning, of course, they just require many human interventions, right? They require quite a subtle design of the policy set, something like that. And but we think that disentangled learning actually is a way for all. We think that, of course, it's challenging, but from the ideal level, this is a quite fundamental way to realize stable learning, because if you can just learn a representation space that is disentangled or without much collinearity, something like that, then we can solve a lot of problems, for example, the unobserved variables or something like that. But I agree with you that, okay, there are a lot of work needs to be done to do in this line. But the current disentangled learning, I would say that that's just an ideal image, right? We still need to do a lot of work on that. For the deep learning literature, actually, we have do some trials on how to make this kind of sample reweighting strategy into the deep learning. Actually, we have observed some meaningful results there. So if we are trying to, for example, because in today's deep learning, we just regard all of the samples, they are equal, right? So what if we just assign weights to this to these input samples? Then how deep learning can deal with this kind of sample weights? And then we just observe some improvement in their performance stability, but we still need some solid works to analyze why they can do that. Yeah. So that's just what I can share with you about the progress. Yeah.
We'll take that one and come back here before going to the next one.
Along the same lines, do you have any results as to how stable this reweighting method is? And do you have any results as to how it compares, how it ties to PCA, for example?
I'm sorry, I didn't understand. What do you mean by results?
Results as in when does it break down? Why do you think, well, you explained why it works by disentangling partial conditional expectations, conditional probabilities. What are the underlying assumptions? If, I don't know, a distribution stability, or what are the underlying assumptions that make make the method work well for stability, and so that could break it down if they're not assumed.
Yeah. I think maybe there are two kinds of assumptions here. One is just the methods that are developed and based on the literature of causal inference, they just assume, okay, if we can find out the causal variables, and then the causal variables, they just their predictive power actually are stable across different distributions and different environments. So if we can identify these causal variables, of course, we can only use them to make predictions. That will make a stable prediction, right? This is one kind. Another kind is our work. We just think that, okay, we can reduce collinearity. And by reducing the collinearity, actually, we can guarantee the model can generate uniformly good prediction for all of the data samples. So you can think that, okay, if for all of the data samples, your errors are the same, that means you actually don't depend on the distribution form to calculate your loss, right? It's just depend on your samples. So that means we just can do stable prediction. So this two kinds. One is the causal variables are stable. The one is collinearity actually leads to instability, and by reducing collinearity, we can achieve that.
Regarding the stability, one thing you mentioned is uniformly good at all the data points. And not sure if you know, John Doge has a new learning framework about robustness. You assign different weights for the data points, and basically the min-max problem. You tried to learn the model for the worst case. So how do you see the relation between these two? Thank you.
Yeah, that's a good question. Because recently we developing a unified framework to describe or to formulate the. Actually, what you mentioned is a distribution robustness problem. And after some analysis, theoretical analysis, we find that they are quite consistent with the sample reweighting scheme, just in different fields and different lines of research, but they are connected. I think we will just share this research results soon. Yeah.
I have a question about your KDD 2017 paper on where you have these weights beta to identify confounders and their level of confounding, right? Yes, it would be helpful if you went to that slide. Because I noticed that you reuse those same weights beta, it seems, to also estimate the potential outcome. I was wondering what is the logic behind that, if I'm correct in my reading.
You mean these slides?
Yes, exactly. Mm-hmm. So you see the beta reappears in the second, the green box, right?
Yeah. So actually, because you say that y, actually y is partially generated by fx, right? So the fx actually is alpha m here, right? And then, of course, if we can find out, actually the alpha is beta in the next page, okay? So if we can learn a good alpha that can just optimally predict f, then we will think that this alpha actually is a generation coefficients, right? So that's why we use this kind of regression to estimate the optimal beta.
Okay, so
right.
it's the potential outcome under control only.
Yeah.
Right. So only the f of x term, which is also why that was my related question. Why you the summation is only over tj equals 0.
Yeah. For this prediction, actually, we consider both the treated and control group, right? Because, for example, if you just use this is a control group, but after weighted, actually is a treated group.
Right.
So
but
the
your summation only runs over the actually treated people.
Yeah, because this is ATT.
Yes.
Yeah.
Sorry, the actually control people, right? T equals 0?
In the treated group. Because you just use the W to approximate the treated distribution, right?
Just one small question. T equals 0 means control, or?
T what?
T equals 0. TJ equals 0?
Yeah, TJ equals 0. That means this is a control group samples.
Okay.
Yeah.
All right, thank you.
Last question.
Thank you for the very informative talk. So in your work in stable learning, you assume the causal mechanism is invariant or only use the invariant part of the causal mechanism. And I know there are some work in causal discovery, they don't have such assumptions. And they try to do adaptation, like in different domains and in non-stationary time series. So my question is, do you think the invariant mechanism assumption is valid in most scenarios? And whether, if we consider the change of this causal mechanisms, can it be more general and more stable in more stable learning?
Okay, thank you. I think when we talk about the stability or generalization ability, we must have a scope, right? So for example, you cannot imagine that we just using the causal factors in mathematics learning to improve our English learning, right? So that's actually two totally different domains. So when we talk about the distribution change or environment change, of course, there are some under hypotheses that, okay, these are just in the same field, and they share similar data generation process. But only the problem is if you only have the observed data, whether you can estimate the true model. So if these two domains, they have different true models, then actually they go beyond the scope of the stable learning, right? So I think it's correct that maybe in different domains we need to adapt the causal knowledge. But in that sense, actually, the true model is not stable. So that's not the scope of us. Yeah.
So from my knowledge, I know such works like they assume py given x can also change. And they also have the identifiability unproved.
Yeah.
Yeah.
Yeah. In that sense, of course, you need some other auxiliary
There's some
information.
mild constraint on the relationships between them.
Yes.
All right, thanks for all the great questions, and let's thank the speaker again for an awesome
Thank you.
talk.
Thank you very much.